So we'll start with the TA. We'll start with the homework 1. That was not supposed to be there because I started that part. Okay. In difficulty, how was the homework for you? Can you put a message in the chat from 1 to 10? How difficult you thought the homework was?
I think it's 8.
8. Okay.
I think.
Put it in the chat. Everyone, put a message in the chat with a number between 1 and 10, rating the difficulty of the homework, being 10 impossible and 1 very easy. Okay, so a lot of 8s. Okay, 8, 8, 8.
It fluctuated. Some questions were like a 5, some were a 9.9. It just depended.
Okay, so the part 2 was very difficult. It seems impossible. 6. Okay. So it seems that people that are engineers found it not kind of difficult, and yeah, someone thought it was very easy. Yeah, I think it was easy. We started very easy in comparison to the other semester. In the last semester, the first homework was not near this homework. It was very difficult in comparison. So why I'm asking that? Because now that you know the difficulty of the homework for you, you're gonna start having some time planned to answer it. And for the people that found homework 1 difficult, the homework 2, in my opinion, is a lot more difficult. So I don't know, 1.5 times as difficult, something like that, because the second part is not trivial at all. But we'll be discussing about those parts. Okay, so for the first problem of the homework, we had a linear transformation, T, that maps a vector in the 2D space to another vector in the 2D space. And we had the linear transformation evaluated in E1, the canonical vector in the direction 1, and E2 gives B1 and B2. So the first question was something we answered in the TA. So I will not be explaining the theory, but I'll be showing an example. Here I have a code that imports NumPy array and concatenate. And here, with the list comprehension syntax, I'm doing a list of arrays. Which points are these arrays? The blue arrow, the blue crosses. So I have a point 0, 0, a 1, 0, 1, 1, and 0, 1. Okay, 4 points. Here I define the vector B1 and B2, and then I define a matrix that is the concatenation of B1 and B2. That was the relationship between the B1 and B2 and the linear transformation. Then what I do is plotting the image of the linear transformation and also the pre-image, or just the canonical vectors and these other 2 vectors. And as you can see here, for the transformation matrix, that is diagonal, and in the x direction it has a 2, it dilates in the x direction until the square here, the blue square, gives you a rectangle that has 2 times the length. That's why you have a 2 here in the diagonal. If I put a 2 in the other direction, it will give me a rectangle. Sorry, I need to run this again. But in the y direction. So now it's a rectangle that it has 2 times the height. Okay. Rocio, are you with your hand raised because you have a question? Or you just forgot to put it down? Okay. Okay.
No,
So,
it was before.
okay. So, basically, that happens when you have a diagonal matrix and you apply this kind of transformation. The terms in diagonal tells you how do you stretch this square. If you have different values in the diagonal, for example 3 and 2, you will copy 3 times the width and you have 2 times the height. Now, what happens when you start adding stuff in the non-diagonal terms? For example, a 1 here. I am recording the class. But it's not automatically in YouTube. Okay, so what was it? Okay, see, if we add a 1 in the parts that are outside the diagonal, and we run the code again, as you can see now, instead of only having a transformation in the x and the y axis, you also have a shear motion. If you don't know, shearing is when you have an object and you apply forces in the upper part and in the lower part or the bottom part, but in opposite direction. So instead of having a rectangle or a square, you have a parallelepiped. Okay, so you have something like I think I'm showing here. Okay, so the first question, if I remember correctly, was what happens? Oh no, that was in the second one. Okay, so that's basically what the transformation T does. Now, what happens if B1 and B2 are linearly dependent? As you have the vectors, something I forgot to explain is that the directions of this parallelepiped are exactly B1 and B2. As you can see, this red point here is exactly B1, and this point here is exactly B2. So what happens if they are linearly dependent, or in other words, that one is alpha times the other one, or they are pointing in the same direction? That means that your parallelepiped, it will start getting squished until they have 0 area. So here, now the vector is 1, 1, so that's why you have a line in the direction 1, 1. If this V1, instead of 1, 1, is 2, 1, the squished parallelepiped will be aligned in the direction 2, 1. If I instead put 0, 1, it will give me a vertical parallelepiped, a vertical squished parallelepiped. So it doesn't have any area now. All the area is squished in the points. That was the answer of what happens when both are linearly dependent. Both the two things happen, the area disappears, and the direction of the line is equal to B1, or alpha times B1. For the second part, you needed to express the area of the parallelepiped in function of x and y. So here I don't have code because I wanted to show here my little notebook. And basically I have x and y that later will be B1 and B2, and I have this parallelepiped. So the previous TA, I said that the area of this triangle, this area, is equal to the norm of x, the norm of y, and sine of the angle between them. And here I'm putting an absolute value, because otherwise you could have negative areas, and that does not make sense. But the triangle is 1/2 of that. Therefore, the area of the parallelepiped is just this part here. And how do you get sine of theta in terms of x and y? I told you that cosine of theta is equal to the inner product between x and y, and you needed to divide by the norms. Okay? And how do you get the sine? You need to remember that cosine squared of theta plus sine squared of theta is equal to 1. What that means is that minus 1 sine squared of theta is equal to cosine squared. Sorry, I wanted to show the thing in terms of sine. Okay, cosine, sine. Then you apply the square root, and when you have a number that is squared and you apply the square root, it's not true that you just delete the exponent. Okay, it's not that. You need to have the absolute value of the sine of theta. Why? Because if you have, for example, minus 1 squared, that is equal to 1. And if you apply the square root of minus 1 squared must be 1. But if you just delete those, you'll have minus 1 equals to 1. That obviously does not make sense. So it's equal to the absolute value of minus 1, and that's why the equality holds. And here you have 1 minus cosine squared of theta. Okay, and cosine was this thing here. Then the sine of theta equals to square root of 1 minus parentheses the dot product between x and y, the norm of x, the norm of y squared, and then what you need to do is or just it's easier if I just multiply, because if I multiply both sides by the norm of x and the norm of y, I get that the area, or the norm of x, norm of y, absolute value of sine of theta equals to this term here. Let's call it a, just for have a simpler notation, a, and you have a here, x, y, square root. And when you have something like that, you can enter the a squared. So now you have a squared minus a squared, and the inner product of x and y squared a. Okay, so if you see, the squared is distributed in the inner product here and the a. So this a and this a vanishes, and the final result is square root of this minus this. And at the end, you only had to evaluate x equals to b1 and y equals to b2. Okay, sorry for going so slowly, but I wanted to be sure that everyone understands this. Rocio, do you have a doubt? Or Pablo?
No.
No? You have the hand raised.
I don't know how to.
Okay, Paulo, do you have any doubts?
No.
No? Okay, so I'll unraise your hands. Now, should be fine. Let me move this. Ah. Okay, so I'm not being able to drag the thing, so it will remain there. It doesn't matter. Okay, next part. Everything clear in this part of the solution?
Yes.
Yeah?
Yes.
Yes.
Okay, nice. The other part is explaining your own words. What does it mean when the area of the deformed cell is strictly less than 1, equal to 1, and greater than 1? So I'll explain it in my words. And basically, if you had this tiny mass element and you apply the transformation T, for example, this could be the result of the transformation, and obviously, because it's the same square, you'll have the same mass. You have this mass here and this mass here. But here, you have an area A1 and an area A2. That means that the density of the first element, or the red element, is equal to the mass divided by the area, but the density of the second one is the mass divided by the other area. That results that if the area of the second element, as the area 1 is 1, because it's is the one you make with the canonical vectors, 1 0 0 1. That's why it has area 1. That means is that if you have A2 greater than 1, A2 greater than 1, the density will be less than the first one. If the area is equal to 1, the density of the transformed body will be the same. And if you have that the area is less than 1, you'll have that the density of the second body is greater than the first one. Okay, so for example, the blue parallelepiped is it could be, for example, this term when the area is bigger. But you could also transform the body so it remains the same area. For example, you could do something like this, that it has the same area but it's rotated. But you can also do something like this, that you have a tiny parallelepiped, and as you conserve the mass, the density of the object must go higher. Okay, that was the solution of that part. You didn't need any formulas. This kind of explanation is correct. You could have drawn each parallelepiped with the different cases and explain what happens with the density. So that was the solution of that part. Any doubts before we start with the problem 2? Someone had this part incorrect or wants an explanation? Javiera, I saw you.
No. I understand the part 1, and the part 2 about the epidemiology is more logic, I think, for me.
Okay, so
Carlos, the only thing is, I think that the shape is a parallelogram because it's 2D. The other one that you say, the parahelium, this one, I think is 6 parallelograms together, like in a 3D space. I think.
No, no. Parallelepiped is when you have a 2D shape, but it has the. Oh, you're right. It's in 3D. I'm not sure how to say it in 2D. I thought it was called like that.
It's a parallelogram.
Parallelogram?
Yeah, because I
Okay.
yeah. I mean, it's just the word, but
Yeah, that's good. That's good for me. Not even in Spanish, I know the difference, so now I know.
And it's easier to say parallelogram, so for the future, yeah.
Yeah, that's true.
Easier word.
Yeah, but I will say that the vector x could be in 3D, and that's a parallelepiped. Just being stored. Yeah, it is a parallelogram. Then let me be sure. Yeah, parallelogram. It's easier to say that. Okay, thank you. Okay, so before we start with the second part, I was going to say that this part was made by me. So the people that found it more difficult, I'm sorry, but I tried to add code and think and stuff like that. And as obviously we are in a pandemic, I thought that it was very good to try to analyze the data. This data that we send you for the homework is the data of all the countries in the world, of the total cases of the virus. This is not made up. This is actual total cases confirmed for each country and in each time. And at the last part of the homework, I had a link. If you were watching carefully here in assignment 1, okay, and this link here, or our world in data, you can see all the data that is available about the virus, and you can see the growth of the total cases in the world, and you can filter depending on the country, and this is updated, so you can enter one day and the other day you'll have the new data. And this does not have anything to do with the homework, but I just wanted to show this page because it's very good. It's not only about the coronavirus, but about data in general. Now it's full of coronavirus because obvious reasons, but in other time periods have different information about climate change and stuff like that. Okay. So now, let's start with the second problem. There was two ways of importing the data. One was just to use the pandas, but the other way was to read it as a text file, and I showed an example in the test, so I will not go over that, but I will be showing pandas. If you use pandas, that is a very good library for data analysis. You have functions as read CSV, and you can put the CSV file there, and after you load it, you can display it in the notebook and have it with the column name. For example, the columns here was ID, entity is the country, code is the code for the country, and the date that it happened. And here you have the total cases. So if you go down, you can see the different countries and with the different numbers. It even has the world. So for example, for Chile, what you can do with pandas is to search all the data that it has the code. Remember that code was the abbreviated version of the country name. So for example, for Chile, it was CHL. So this means all the data that it has the code Chile, you can filter the data and assign that to a variable. Here I called it CHL. And then this ch, yes.
Carlos, I have a question about the pandas. Is more in the for the next homework? Is better work with pandas or no?
I'm not sure because in the case of the second homework, I did the part that you need to program. I also did it, and I did it in a TXT with no apparent format, so I'm not sure if you can read it with a bit CSV, but
Okay.
you could read it with another function maybe. I think you could import it with NumPy.
Okay, thanks.
Yeah. Okay, so for the second homework, try to do it with pandas, but if you don't, if you can't do it with pandas, try to do it with NumPy. But now that you already learned how to do it but by hand, you're gonna skip that part. And okay, so let's continue. With, if you have the data that only has the code Chile, then you put total confirmed cases, that's the name of the column. It's a long name, but that's it. And you'll have a variable here, total Chile, where you'll have all the data for Chile, and if you plot it, you'll get something like this. Oops. For example, here it says name error, name data is not defined. When something is not defined, it's probably because I forgot to run a cell. So if you go to this cell and I run this again, and then run the second part, now it displays the plot. So that was an example of how to debug the code, and that's the exponential for this country. Okay, now for the second part, this was not as obvious. So let me write something. Okay, some of you got that this was exactly the same example I did in a last TA, but for the ones of you that didn't saw that example, basically what you had is a lot of points x and then a lot of points y, where y is the number of cases and x is the time. Okay, so I'll abbreviate all these points with vectors x and vectors y, and for each country that was the subindex j meaning the country. Okay, you had one of those vectors. Now, one thing that was challenging in the part 2 was that you had to have a linear system. For example, a times a vector beta plus an error equals to a vector b, where b, these are vectors, was equal to the logarithm of this vector, meaning this operation is pointwise. Pointwise mean, for those that don't know, that each element, for example, the first element of the vector is assigned to the other part, like this: logarithm of y1, logarithm of y2, logarithm of yn. This logarithm is the natural logarithm. So that means that log of e is equal to 1. When something, when I have a logarithm that it has a different basis, it will be clearly specified as logarithm of that base. Okay, and okay, that was it. And now for each country, when you already have this vector b, so you'll have a vector b sub country with the specific data for the country, and you had to do something like this. For each country, you had to do a linear fitting. And the challenging thing here is that each country, for example, this could be Chile, but China started a lot of months earlier. China, and I don't know, another country started later. So it doesn't make sense to try to fit a line like this one in this case, because you'll have a lot of data that doesn't fit. So you have to do a fitting here and here. In practice, what that means is that you have a line that is m times x minus an offset. Let's say that the offset is a plus n. This is for the country 1. So you have a data 1 and offset 1, and you have m1 and 1. For the second country, you have a slope that's different, a position of that line that is different. That's what I'm calling the offset. And here you obviously have the error term. And I forgot to do the arrows. Plus n2 plus the vector of errors 2. Okay. So as you can see, it seems at first that those two models cannot be represented with the same matrix A. But that is not correct, because you have this. I'm deleting the index, sub-indexes, because it's easier. You got something like that. You can always write it as, oh, this is not a vector, by the way. You can always write it as m x plus n minus o m. So this part here could be represented as another intercept, basically. Changing the height of the intercept is the same as changing the time. And what that implies is that you can have y. Oh, sorry, I meant in the previous part, these are not y's, are b's. This is a b, 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 because they have a logarithm. Sorry about that. So this is a b, 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 and b. So it doesn't matter how the data is, you can always put it as this: b times, the vector b for the country A is equal to some slope times the vector of times. Sorry to say time a lot of times. That corresponds with not this country, but a universal time. And then you have an intercept, because any offset here you can put it to the intercept. So that's why you can put just a vector x, and this vector x could be any that you want. For example, 1, 2, 3, 4, and so on. So here you have m, 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 plus n, plus n, plus n, plus blah. Okay, so I'll stop there. And here you have b, j, comma 1, b, j, comma 2, b, j, comma 3, and so on. So now, what's the matrix? As you can see here, you have a vector m sub j, n sub j. That's what I've been calling beta, the parameters for the country j. And now, as the n's here repeat all the time, to the second column you just put ones, and for the first column you put 0, 1, 2, 3, and so on. That's the matrix A. And this matrix A is the same for every country. It does not matter which country is it, this will always be the model. The matrix model, the linear fitting problem. Linear fit. And here this will be equal to the vector B. And you also have the error term. This is the error term. Because in each of these equations, the logarithm of the data will not be exactly the slope. What that means is that if, for example, I have the points that represents B and the time x, and you, for example, have this line with a slope of m and an intercept of n, the value between the real data, this point, and the slope will have a little deviation, or big, depending on how good is the fitting. And the length of this is what we call the errors. For example, this length is E1, E2, E3, E4, E sub n. So that's why you need to add an extra term with the errors. And now that you have all that, what your problem, minimizing the error. You want to minimize the error. So if you have, for example, a vector of errors, you can just put E sub n squared. And if you see here, how do you do this operation? This is the same as minimizing the norm of A times beta minus the vector B, the norm 2. And this 1/2 is just an additional term. But basically what you're doing is minimizing the errors. Minimizing the errors between your data and the linear fit. That's what you're doing with your model. Okay? And how do you do that with a computer? We have a lot of theory, but let's start doing it. Okay, so that was the solution of this part. And the dimensions of A, beta, and E are the number of data points that you have times 2, 2 times 1, and n times 1. That was the solution of that part. Any doubts? This was a little bit more confusing than the previous parts. Everything clear then? Okay. Rocio, do you wanna talk?
Carlos, can you show the previous?
This one?
Before this one, when you added the errors for the first time.
This?
Yes.
Yes, this one. Okay. You just wanted to see the slide?
Okay, because I forgot when you added the error, but now I found it.
Yes, here.
Here, see.
Or here.
Now in the second one.
Okay. Obviously here you also have an error term. Okay, everything clear? Or I'm sure that not everyone did it this way because I watched the homeworks. So everyone understood why it is this way?
I think originally I didn't get the importance of minimizing the error. So it's nice that you explained that. Yeah.
Okay, yeah, that was the hidden meaning of of the optimization. That you are minimizing the errors of the linear feed.
And Carlos, is there also sometimes a process where the big, like you can work out if an error is so big, you remove them?
Yeah, of course. Yeah. But that in most of the time you just delete the data. For example, if you have your line and you have a data point that is here, if you add that point to the linear feed, probably the line you'll obtain is something like this. Yeah. But most of the data is not well fit with that line. So that's what it's called an outlier. And when you have an outlier, you just remove it from the data.
And you do that before the line is drawn?
Yeah, before any of this part of the optimization problem, you delete that point. You can put it as a none or missing value or...
Okay, thanks.
Or another thing that people do is that you can put it with the mean of the previous and the latter one. But when you have a traveling point, it's just easier to delete it. Nobody will miss that point.
Nice.
Well, if you have a lot of points, you can do that. Okay, if you have 2 points and you delete one, is obviously a problem. Okay, so this next part is about how to do that in the computer. But first, how do you minimize this problem? I explained in the TA previously, but I will explain it again. This problem here, when you are trying to minimize this, basically what you have is a quadratic problem. Let's put it in 1D so it's easier to understand. So your function is this green function. You'll have something like that. So f is this green function here, and the minimum is this point here. And you are interested in this beta star that minimizes the expression, where here you have an f evaluated in beta star that is equal to something. Okay? And this is a quadratic problem. And to solve a quadratic problem, you can see where the slope of this is equal to 0, and that will be the minimum. As these have a norm, this will always be a quadratic pointing up. It will never be something like this. The problem with this case is that if you find the part where the derivative is equal to 0, it could be a maximum. But as the second derivative of this function, it will always be positive. You can, with all certainty, say that if you find a point where the derivative is equal to 0, you'll have the minimum of the function. And also, that property that I just said is satisfied because this f is what it's called a convex function. What does mean that the function is convex? That if you paint the upper part of the function, the resulting blob will be convex. Okay? So if this part that is called the epigraph of a function is convex, that means that the function is convex. And the norms are always convex. So we have that. We can do the derivative of this function without having trouble. And if you do the derivative of this function with respect to x, that is equal to applying the gradient of the function. And these two goes down multiplying. That's why I put the two dividing, so it will cancel out. Then you have the transpose of the matrix A, and A times B, B. Why does this matrix appears? Because with the analogy of your 1D problem, basically what you have is a function like this. So if you do the derivative, you'll have A times what was inside. Okay, but now as you have a matrix, for the dimensions to be correct, you need to put the matrix transpose. And as I already explained, this will give you that the point where this is equal to 0 is the beta star. Beta star is when this is equal to 0, and the point I will not skip in any step, sorry. I was just going to put the solution, but if you want to solve this, you'll have this. Then you apply the inverse of this matrix from the left, and you'll have the beta star is equal to the inverse of that part transpose B. And that's what we call the pseudo inverse. Or A plus. That is very similar to the transpose, but it's not. Or sword. Another. That's a pseudo inverse. And you can do that by calculating this matrix or by doing least square in Python. Everything clear until now? Yeah, no one's talking because everything is very clear or because they don't understand? To get full points? Sorry, can you explain your comment? You had to do both proceedings? No, you could just apply the least square problem. So for example, here you had to do from numpy lineal import least square. It seems that it auto-completed the thing, so you can autocomplete with this notation if you imported the package first. And A, our matrix, it was a matrix full of 1s in the second column. So you had a 1 there, and what was the size? What was the length of Chile? No, it was called total Chile. Okay. Total Chile. For example, here print n 26. So 26 was the number of points here, where Chile was different than 0. You could see if Chile is different than 0 by doing the total Chile equals 0. So here you can see that not a single point here is equal to 0, and you can trim the interval. Also, I said that you needed to remove the points past the quarantine on each country. If you didn't that, I'll let it pass, okay? Don't worry. The linear fit will not be as good, but as is the first homework, I'll be a little bit more soft. And I'm not completely sure how to do this with pandas, so let's try to put it as a list. It's better like that.
Sorry, Carlos. Maybe I missed it? Did you explain how you pick the optimal sample to find the pre-quarantine?
Yeah. How you do it? Is by applying the least square function.
Okay.
And why you needed to apply that instead of the inverse? Because as we saw before, the matrix here, it has a lot of equations, but only 2 parameters, so it's not a squared matrix. That's why you needed to do the least square instead of just doing the inverse of the matrix A.
Okay.
And we import the least squares here, and oh sorry, I forgot to make the matrix. Okay, so this is a very easy way to make a matrix. You do an array of this, and for n in range n. If you look at the matrix, oh sorry, I put 2. It must be a 1. As you see here, this is the matrix that we already discussed, from 0 to the number of points minus 1, and the second column is just 1s. This is a very...
Sorry, Carlos?
Yeah?
About the matrix, day 0, we consider day 1 or 0?
It doesn't matter. If you consider this as 1 or this as 10, it doesn't matter.
Okay.
It will give you the same result.
Thank you. Okay.
But yeah, if you use now the least square of the logarithm, okay, so you need to import the logarithm. Just to be a little bit more organized, I just put logarithm of, this will be our y. Logarithm of y, and this word is not defined. I added an extra s. Okay, so this part here is just a warning, it doesn't matter. But the first part here is the important part, and those are the parameters. This is the slope, and this is the intercept. So, for example, just to be 100% clear, let's put m slope intercept equals to that. And now, if you wanted to plot both lines space, but it was not required for be continuous, but okay. Line space from 0 to n and endpoints, and that's our x. And from matplotlib, pyplot, import, plot x, and b plot x, and this was exactly the same as the TA. And as you can see here, we have this warning. Remove this. It's not cropped. There. You can see here we have our data in blue and our linear fit in yellow, and the difference in height of these 2 points is our vector e. So if we wanted to calculate the vector e, it would be b mn minus n, and this is e. And for those of you that have applied linear fit before, for example in Excel, you'll have a number that is called the r squared. That's directly related with this e. And if you, for example, sum these squares, absolute of e and u to the square, I need to import the sum. Sorry. And this notation with the dot is not in Python. It's about 4. So the value of our function in the optimum is 4. And that's the same as the norm of a beta minus b. This number here is directly related with the r squared. To get the r squared, you need to divide by something that I don't remember right now, but you can see it in Wikipedia. Okay. Any more doubts about the homework one? I'm not sure if I missed something. Okay, I missed something.
I don't know if you can you hear me?
Sorry, let me finish with this part. So for the second part, you needed to see in which time population of Chile. Okay, so the population in Chile is this amount, and you needed to see when this beta, that is x times m plus n, would be equal to the logarithm of this, or to the 6. And basically, to have that, you need to solve this equation. M times x plus n is equal to the logarithm, and you basically needed to subtract n and divide by n. Okay, so your tau for Chile is equal to that. 53 3 days. So if you divide by the number 30, it would be approximately the number of months. Obviously, you had to do something a little bit more complicated than this, but if the starting point was some date, you add the number of days and you get another date. And that was the solution for this part. You need to calculate this tau and then see which one was the corresponding date between the start and when you add this tau. I use the datetime library. Yeah, with the datetime library, you could probably convert this to a date and do it automatically. Just to know, Benjamin, how did you do it? Do you have a code example that you can put in the chat so everyone can see it? Okay, well, it's not that important. Okay, if you didn't put the date but you obtained this tau correctly, it's not the end of the world. Okay, the important thing is that you understood what you needed to do. And here, let me erase all this part. If we put 60, sorry. Okay. It doesn't want to work. Probably I changed something. No. Okay, so basically what you're doing there is to obtain. Okay, so you have all your data points. You already obtained a linear fit to the logarithm, and then you have the number of cases, and at some point you have the total number of people in the country, and you have time. And basically you have a tau here where if you projected this line, it will give you the total number of cases. So you basically needed to do n equals to m tau plus n, and therefore this n is the logarithm, by the way. This is the logarithm of the number of well, the number of people of the country or the population. Logarithm n minus n divided by. So that was the number. Okay, everything clear until now? What time is it? Sorry. So I have time for the. Oh, we don't have a lot of time, so I'll go a little bit faster for this last part. I missed something. Oh, in this part it also asks you what's the amount of days in which the total amount of cases doubles. For that, you have your slope, your intercept, and this is obviously the logarithm of this data. You needed to find x plus delta x or delta t. So this thing here is equal to 2 times the number of cases. Probably this is easier if we do the exponential. This will be that, and 2 times e to the mx plus n times e mx. So if we divide 1 and 2, you'll have 1/2 here, and those numbers will simplify, and you obtain m times this part here. So if you apply the logarithm again, you have the logarithm of 1/2 is equal to m x, and you basically had that the amount of days, the number of total cases doubles is equal to the logarithm of 1/2 divided by m. Okay, by having set a code, so you could transform your results to dates. So if anyone wants to see that, and that was basically the homework one. Carlos? Yes.
Yeah. Is that number 1/2 going to give you a positive result? The log of 1/2?
Probably not. But if it gives you a negative number, it doesn't matter because it's the difference between the times. You're just taking it in reverse order.
Okay.
Yeah, it doesn't matter.
Okay. And another question is that when you took like different data points, the curve or the approximation that you would get is very, I don't know, it's like very dependent on which data points you took.
Yeah.
So when you revise the homework, are you going to consider that in any way, or is it just you have to get it right? I don't know.
No. I will not be strict for this homework. I'll be very relaxed. If you added a linear fit to some interval, it doesn't matter which one.
Okay.
And if you did it correctly, you'll have all the points. It was not specified as an absolute thing. It was more try to do your thing. I knew that a lot of people could choose different time points. The main thing is that you do this linear fit to the logarithm of the data, because I saw in the homework that some people, maybe without wanting, they did the linear fit to the exponential curve. So that kind of thing will subtract points, but not if you choose an incorrect interval. There's no incorrect interval. Okay. Any other doubt about the homework one, or we can go to the second homework? Now we have time for the second homework. Yeah, everything clear then? Okay, so have you read the homework? Raise your hand. How many of you have read the homework? Yeah. Who said yes? Sorry, I didn't quite get.
Yes.
Carlos?
I read the homework.
Javiera. Do you have any doubts?
It depends of the. I read, but I try to unit about the classes in with Carlos, but yes, I think it's more difficult than the previous homework. So
yes, it is, and a lot.
Carlos.
Carlos. Yes, Carlos.
I have a question. And number one, when you say show by a direct computation, is that just like a mathematical expansion of what we have and then just solving, or do you want us to like do a matrix A, do a matrix B, like a numerical number, and then compare?
No. Like theoretically, I want that.
Oh, okay.
If you have, for example, a matrix A that it has components A11 and so on.
Okay, perfect.
A21.
So
I'll explain a little bit for the rest, because I'm not quite sure if all the people got this problem.
Yeah. Sorry, it's just that I have another class now, so I just wanted to know that quickly. But
okay. Yeah.
If the rest needs some explanation, that's fine.
Okay, but
thank you, Carlos.
I wanted to talk about the second part of the homework because that's the difficult part. Or this one is kind of easier, but the second part you need to do a lot of programming. But just to be clear, when you multiply two matrices, I'll try to do very quickly. You're basically multiplying the rows of this one and the columns of this one, and it will give you a point in the matrix C. In the problem, with what they tell you to do is to calculate the trace of A transpose B. Okay, the trace is that if you do all these calculations, the trace is the summation of all the parts in the diagonal of C. So the trace, if this is a matrix C, is equal to the summation of these little c's n from n to 1 to n. Okay, and by doing the summations, you need to get the formula shown here. That. Because I'm not sure if everyone knows what the trace is, but you just need to add up the diagonal entries. This is explained, but well, it's explained in the homework, but just to give you a little bit of intuition. The first problem is a lot of theory and just calculating summations and stuff like that. And it defines an inner product in matrices, sorry, that is like this. And then you can show that some matrices are orthogonal and so on. And the second part that I wanted to talk a little bit before finishing the TA is a little bit more complicated because you needed to define, for example, if you have a curve like that, this f is a curve that is defined in a parameter t. For example, here is with t equals to 0, t is equal to 0.1, but at the end, t equals to 1. And this is defined as a lot of points that has coordinates x and y. Okay? But in the homework, this is written as a complex function. That means that the parameter now is from reals to the complex numbers. And the function that we are defining with the parameter t is now as the real part, the coordinate x, and as the imaginary part, the coordinate y. And as this function is now a function with one parameter and complex image, we can calculate a Fourier series. What that means is that we can approximate this as a summation of exponential functions, some coefficients and exponential functions. Cristóbal.
Hola.
Hola, estás de ¿cómo se llama? Oyente.
Ah, es que pensé que la reunión era a las 3:30.
¿Son las 3:30?
Creo.
Sí. Oh, okay, so I don't have more time. I lost the track of time, sorry. It's the time to finish the TA. The second part is a little bit confusing, so if you have any doubts, you can send it to me via Canvas, okay? And let's have a little 5 minutes of questions, if any of you have questions of the second homework. If not, we'll give this TA as done. Daniel, do you have any doubts? Javiera, Christine, Pablo?
Carlos, yeah, the only question I had was, does this shape you've done, does this relate a little bit to in one of the first tutorials you talked about that dragon thing?
No, no, that will be too difficult for this course. No, it's not related with the dragon curve. Actually,
Okay.
when you load the files, you'll see that one curve is, I don't know, something like this. Another curve is like a heart. Another one is like an infinity symbol, and another one is, I don't remember, something like this. Okay, they are very easy, and you need to do the Fourier series to approximate these curves, and you need to say how many coefficients of this series you need. And
with these kind of tasks, theoretically, it definitely makes sense. It's just sometimes it's a bit hard putting that into practical terms, you know. But
yeah,
I guess
that's the challenge.
It's a kind of.
And well, if you have any doubts, you can contact me. But the second, this is like the first part of the second question, but the second part is a lot more difficult, and the curve is something like very complicated, like this. And the curve is actually the trajectory of the moon, as seen in Chile. That means that if you look up at the night and you saw the position of the moon every night for a lot of years, and you then trace the trajectory of the moon, it will do something like that. And well, you'll have time to read the homework more carefully later, but basically what you need to do is try to do the Fourier series of this trajectory of the moon and associate that with the epicycles that are written there. That was a concept that Ptolemy in the 2nd century described as the motion of the moon and Venus and Mars and all the planets, because he thought that the Earth was the center of the universe, so every planet trajectory was described as something very complicated because the Earth was the center, and all the bodies in the solar system, with respect of the Earth, does something like that, not just an ellipse. Okay, I'll be finishing the TA now. Pablo is suggesting to do a group chat. There exists a group chat for the IBM, so Christine or Rocio or someone can include Pablo to that group, or the other people, please. If all the people can say your cell phone, so you can have a group where you can all talk. If you add the new people to the IBM group, I will be there. So if you have questions, I can answer there. Okay, so if someone wants to say their phone number, so Christine or Rocio or someone adds you to the group, you can say it right now. Rocio, you're talking with me, not Pablo. Okay.
I see.
Okay, I'll stop the recording.